Welcome to this class about data stars. In this video we're going to look at an example of supermarkets and compare their transactional versus analytical business requirements. We will show you that relational data structures are complex, and we will introduce data stars as being a much simpler form of data structure appropriate for analytical questions. So, let's look at the example of a supermarket, and particularly let's look at the sort of data that is generated when a customer goes to the cashiers and the computer system starts to generate a bill for their purchases. For example, the computer will be looking up prices. Every barcode that's scanned will change the stock control. It will be calculating the number of loyalty points to be credited to the customer's account. For some products, it needs to total up the amount of tax to be collected. Very definitely, the computer will be adding up and displaying the total amount spent by the customer as the items go through the checkout. And then when all the items have gone through, the computer is going to have to interact with the payment or the credit card system. So, within a space of just a few minutes, the computer system is going to have to interact with many forms of data. All this processing requires a complicated database system. This database system must be able to almost instantly retrieve information about individual people, products, and purchases. Even a small delay in processing would be critical, as queues would develop and customers may well walk away. But now, let's switch focus to a management point of view. Managers, perhaps in the head office, are going to want to analyse not individual sales, but sales overall, like which branches are doing best, or which products are selling well, and on what dates, for example what months or what days of the week are sales best. This business analysis may well be on a national scale, and you might have thought that scaling from a single shop into all the different branches across the country would make things a lot more complicated. Fortunately, and as we're going to show, that's not the case. We can actually design much simpler data structures for analytical processing. Have a look at this, a simple star, and let's see how it works. We will do this by looking at the first row of the data. This row gives information about sales values in one of the branches of our stores. On date 101, which was 1st of January, in the branch 201, which was the Sheffield branch, and for the product 301, which was drinks, we sold £10 worth of products. Before we move on, it is really important that you understand the level of detail shown within this simple star. The row that is highlighted represents sales information aggregated to the level of the whole day for a whole shop for a particular product group. Notice there's not even a record of which customer bought this because it's all the different customers together. This is the collective record for the day, shop and product group. And the reason we are constructing a model at this level is because for a particular investigation, the business analyst is only wanting to look at the overview. They're perhaps wanting to look at sales over various days, the trends of the sales. They have not asked for specific detail. Now let's look at a second sales record. On date 102, which was the 2nd of January, we sold in branch number 204, which was our London branch, product 303, some crisps, and in total customers paid £50 for that. Are you seeing how this is working? Now, test yourself. For the row that we've highlighted, can you work out what date, what branch, what product, and how much was paid? Pause the video and repeat to yourself what you think the answers are. And now try a similar test, but without the arrows. For the row that we've highlighted, answer now what date is involved. Which branch was involved? What product was sold? And finally, how much was paid? We are thinking that you should have replied that on the 4th of January, in the Cardiff branch, for drinks product, £19 was paid. And now we're going to work the table the other way round. Look at this screen and find which day's sales value happened to be £86, and be ready to answer the next few questions. What are the name of the date on which £86 worth of products were sold? In that sales event, which branch was it that sold £86? And finally, what product was being sold? We think the answer was the 6th of January, unfortunately we don't show this on the screen, in the Leeds branch, and it was fruit that was being sold. We're hoping that you're agreeing that this is a relatively simple data structure. Now let's look at some of the terminology or some of the words that describe them. The 3 tables highlighted are dimension tables. Dimension tables each describe what's going on at the time of the event. For example, which date, or which branch, or which product. Our star happens to have 3 dimensions, but in fact you can have as many dimensions as you want for an analysis. And now let's look at the central table. This is called the facts table. In simple stars there's only ever one facts table. Later, in more complex stars, we can see that sometimes there is more than one table. Now that we've introduced the concept of dimension and facts tables, let's look at each of these again in a little bit more detail. So here we are showing just one of the dimensions, the branches dimension. In every dimension table you ever draw, you must have a key column, normally in the left hand or the first position. And this is so you can refer to each row. You can talk about row 201 or row 202, for example. And then, in every dimension table, there's going to be one, or possibly more than one, columns for describing the data. For example, being able to give the names of different cities. With the possible exception of date, which we'll get to later, always the keys for each dimension table are going to be numeric. Also, and this is without exception, the keys are going to be different to each other. They're going to be unique. Otherwise, you couldn't refer to a row specifically. You couldn't describe row 302 and not be ambiguous about which one it is. Now, in our current example, we've made each of the different tables have different key values. But that doesn't have to be true. Keys don't have to be unique between different tables. You could have a date 301 and a product 301, for example. In contrast, the description columns are nearly always text. The dimension tables could have several descriptive columns. This example has city, county, and country, 3 different descriptors. So again, we want you to answer some questions. Here goes. What is the name of the city that has a key value of 201? You should have said Sheffield. Next question. According to the data, which country is Cardiff in? The answer to this is Wales. According to the data table, which county is London in? Well, according to our data structure, the City of London is in the County of London. In the real world, the City of London falls into 3 different counties, but we don't have a way of showing that on our table. We've chosen this example to show that sometimes this simple approach of dimensional modelling doesn't work. There are solutions, but they are quite advanced, and we'll get towards those right at the end of the module. And finally, we've described cities as city, county and country. Can you think of any other geography-related attributes to help classify different cities? If you can't think of an example, then there are some that we show you later on. So terminology again. City is an attribute of the branch, and so, for example, it's county and country. Whereas the specific values that occur within the attribute, such as Sheffield, Cardiff, Leeds, London, they are all members of the attribute. Whenever you're designing a star, you should design into the dimension all the attributes that the analyst would find useful for doing an analysis, but be careful, be sure to miss out all the attributes that are irrelevant to their query. Now, a moment ago, we mentioned that you could have more attributes. Let's explore this further. For example, you could analyse by the size of the city. Sheffield has roughly 500,000 people, so does Leeds. But that's quite considerably smaller than London. It is bigger than Cardiff, though. Another attribute might be whether it's a capital city or not. You might sell more products in a capital city. You might not. You might even choose to do some analysis based on the number of Premiership football teams in the city. Unfortunately, Sheffield, at the time of recording, doesn't do too well on that score. Notice that nearly all members of the attributes are text. For example, Cardiff, Glamorgan and Wales. But even where they're numbers, like quarter or 1,000,000, these are really just descriptors. They're categories, could be used as labels for different columns on visual graphs. Let's go back to looking at the overall star. The facts table is a list, often hundreds and hundreds of millions of rows long, where each individual row relates to some individual event, such as a sale. On the left-hand side of the facts table, you can see that this example points to 3 different dimension descriptors. Typically, the descriptor is going to be about what, where, when, possibly who, possibly why, for example. And on the right-hand side, we're recording how much. For example, here, how much money was paid. This column is a measure. And it is common in facts tables to have several measures. In the current example, we now show 3 measures. The value of money earned from sales, a count of how many items were involved in that sale, and the amount of profit gained for those sales. So, now as you've seen, as well as having multiple different dimensions, we can also have multiple measures. So, we have presented stars. Let's have a quick look at the advantages of stars. Why use them? And the very first advantage is they are easy to draw and they're easy to conceptualize, even if they have multiple dimensions. The example we're showing has 8 different dimensions. But do you understand it? The second advantage of stars is that in the early days of data warehousing, it was easy to store all these tables on relational database systems such as Oracle or SQL Server. If the company had already invested in a relational database, then a natural way of starting your first building of a data warehouse was to put the tables on the software you've already bought. Relational database systems can very easily store dimension and facts tables, because to relational database they are just tables. And relational databases already have all the facilities needed for creating links between the tables and being able to look up specific rows within target tables. And because of this, stars were a very popular way of designing data warehouses in the early days. The third advantage of stars is about the granularity. In our example so far, we've talked about the products dimension as just having 4 members: drinks, fruits, crisps, sweets. And this is because we assume that our business analysts were not interested in the very detail of sales, but instead were interested only in the overall patterns of sales. For example, whether fruit overall was doing better than crisps overall. But possibly we're wrong in this assumption, and we discover that the business analysts need to explore their data right down at the individual product level. So let's see how that changes our design of the star. Well, here is a new dimension table, not based on products, but based on product lines. And this dimension table has a separate row for each version of the product. For example, line 701 shows Coca-Cola in 30 milliliter cans, whereas line 702 shows the same drink but in 50 milliliter cans. This is going to allow the analyst to see which size of can sells best. Now, a typical supermarket could easily have something like 50,000 different product lines, although not every product line will be sold at every shop. Clearly, the product line table is going to be vastly bigger number of rows compared to the product table. But compared to the facts table, this product line table is still going to be relatively short. We can also see that with product line, there is more to describe about the individual products. So perhaps this more detailed table is going to have a set of extra attributes, not just the weight, but the type of packaging, or even the food type itself. So as well as more rows, there could also be more columns. And now let's have a look at how that changes our facts table. We're still going to have columns for the date and for the branch, but instead of pointing to the product, 301, we're now going to point to the product line key, 701. And because we're recording data at a more specific or finer grain, then the amount of money earned from selling one of these is going to be lower. So perhaps we're only going to get £1 for a sale on a particular date in a particular branch, rather than £10. You can work out, if each date and for each shop, for each product line, there's going to be a separate row in the facts table, then the number of rows itself is going to grow quite considerably. However, it won't go up by a ridiculous number. If a shop happens not to sell a very specific product in any one day, then there just would not be an entry in the facts table. So it isn't as if every single combination of everything that could happen goes into the facts table. Lines only get used up when things actually do happen. So now we can see what's changed. The before shows a facts table with 3 dimensions. The after shows a facts table with 3 dimensions. But the dimension table is perhaps 50,000 times bigger. The facts table will be larger too, but the precise size of the increase will depend on the combination of products that the customers have bought. But the basic star shape remains the same. And that's a major advantage of stars. If a software vendor can make a tool that is good at showing stars, then it doesn't matter whether you're working at the detail level or the overview level, the same sort of facilities are going to work. And once users are familiar with this, they can drill up and down between the different levels. You have already had some experience of doing this when you used the Excel pivot tables to look at different dimensions and different measures and then choose to drill into the data. So, let's have a summary of this class. Stars are much simpler ways of storing data ready for analytical use. You've seen that stars contain any number of dimension tables and usually just one facts table. Dimensions contain descriptions, one row for each object or each thing being described. And fact tables list events, for example a purchase, with pointers to who or what or where or when or which, plus the quantities or the measures for how much. In the next video class, we will demonstrate a star being implemented on a relational database system, and then we'll move on to look at data cubes, which are much more powerful methods of holding the same data. Thank you for following this class.